Here is today's problem. We want x squared minus 2 to equal the square root of x plus 2. The job is to find every value of x that makes the equation true. On the left there is a squared term, and on the right there is a root. That square root is the piece that blocks any direct move. So our first step is to clear the root out of the equation. When two equal numbers are squared, the results stay equal. So we square the left side, and we square the right side. On the left, we are squaring the quantity x squared minus 2. There is a well-known pattern for squaring a difference. It is the first term squared minus twice the product plus the second term squared. The first term squared gives x to the fourth power here. Twice the product of x squared and 2 gives 4x squared, and the second term squared is 2 squared, which is 4. So the left side becomes x to the fourth minus 4x squared plus 4. On the right, squaring simply undoes the square root, so the right side of the equation becomes just x plus 2. The new equation is x to the fourth minus 4x squared plus 4 equals x plus 2. Now we collect every term on the left-hand side. We subtract x from both sides, and then we subtract 2 as well. The plus 4 and the minus 2 combine into a plus 2. So we get x to the fourth minus 4x squared minus x plus 2 equals 0. Every solution of the original equation must satisfy this quartic. A quartic is a polynomial equation of degree 4. Such an equation can have at most 4 different roots. Our plan is to hunt for simple roots first and factor them out. Finding even one root will let us split the quartic into smaller pieces. The rational root test tells us exactly where to look. Any whole number root of this quartic must divide the constant term. The constant term is 2, and the leading coefficient is 1. So the only whole number candidates are 1, minus 1, 2, and minus 2. That narrows an infinite search down to 4 quick checks. We start the testing with the first candidate, x equals 1. 1 to the fourth is 1, and 4 times 1 squared is 4. The total is 1, minus 4, minus 1, plus 2, which is minus 2. Minus 2 is not 0, so 1 is not a root of the quartic. Next, we plug in the second candidate, x equals minus 1. Minus 1 to the fourth is 1, because the exponent is even. Minus 1 squared is 1, so 4 times that is again 4. The minus x term turns into plus 1 at x equals minus 1. The total is 1 minus 4 plus 1 plus 2, which is 0. Minus 1 is a root, so x plus 1 is a factor of the quartic. Now we move on and test the third candidate, x equals 2. 2 to the fourth is 16, and 2 squared is 4. 4 times 4 is 16, so 16 minus 16 cancels. Then minus 2 plus 2 also cancels, leaving exactly 0. So 2 is a root as well, and x minus 2 is another factor. Finally, we test the last candidate, x equals minus 2. The 16s cancel again, but minus x now contributes plus 2. Plus 2 and plus 2 make 4, so minus 2 is not a root. The whole number search is complete, with minus 1 and 2 found. 2 roots are known, but the quartic may still be hiding more. To find them, we divide the quartic by the factor x plus 1. Polynomial long division works much like division of numbers. We divide, multiply back, subtract, and then pull the next term down. First, we write the quartic with every single power on display. That is x to the fourth plus 0x cubed minus 4x squared minus x plus 2. The 0x cubed term is a placeholder, so no column goes missing. Now we run through the division one small step at a time. X to the fourth divided by x gives x cubed, the first quotient term. Multiplying back, x cubed times x plus 1 is x to the fourth plus x cubed. We subtract that product and the x to the fourth terms cancel. 0x cubed minus x cubed leaves minus x cubed at the front. So we carry down minus x cubed, minus 4x squared minus x plus 2. Minus x cubed divided by x gives minus x squared for the quotient. Minus x squared times x plus 1 is minus x cubed minus x squared. Subtracting that cancels the cubes and leaves minus 3x squared. The working line now reads minus 3x squared minus x plus 2. Minus 3x squared divided by x gives minus 3x. Minus 3x times x plus 1 is minus 3x squared minus 3x. We subtract, and minus x plus 3x leaves positive 2x. So the line shrinks down to 2x plus 2, and the end is close. 2x divided by x gives 2, the final term of the quotient. 2 times x plus 1 is 2x plus 2, which matches the line. The remainder is 0, so x plus 1 divides the quartic cleanly. The quotient is x cubed minus x squared, 3x plus 2. So the quartic equals x plus 1 times that cubic expression. We know 2 is a root, so the cubic should vanish at 2 as well. Plugging 2 in gives 8 minus 4 minus 6 plus 2. That sum lands exactly on 0, so the cubic passes the check. So next we divide the cubic by the factor x minus 2. X cubed divided by x gives x squared, the first quotient term. X squared times x minus 2 is x cubed minus 2x squared. After subtracting, minus x squared plus 2x squared leaves x squared. So we carry x squared minus 3x plus 2 into the next round. X squared divided by x gives plain x for the quotient this time. X times x minus 2 is x squared minus 2x, and we subtract it. Minus 3x plus 2x leaves minus x, with the plus 2 intact. Minus x divided by x gives minus 1, the final quotient term. Minus 1 times x minus 2 is minus x plus 2, matching the line. The remainder is 0 once more, so the division is clean. This quotient is the quadratic x squared plus x minus 1, so the quartic splits into x plus 1, x minus 2, and that quadratic product is 0 exactly when one of its factors is 0. The first two factors return the roots minus 1 and 2. The quadratic x squared plus x minus 1 calls for the quadratic formula. Here a equals 1 and c equals 1. The discriminant is b squared minus 4 times a times c. That is 1 minus 4 times 1 times minus 1, so 1 plus 4. The discriminant comes out to 5, a positive number. The formula gives minus b plus or minus root 5 over 2a. With our numbers, that is minus 1 plus or minus root 5 over 2. The square root of 5 is about 2.236, minus 1 plus 2.236 is 1.236, half of 1.236 is about 0.618. Minus 1 minus 2.236 is minus 3.236. Half of that is about minus 1.618, the last candidate. In total, the quartic hands us 4 candidate values for x. They are minus 1, 2, and the 2 roots from the quadratic. We squared both sides at the start, so every candidate gets checked in the original. We begin with x equals minus 1 in the original equation. The left side is 1 minus 2, which comes out to minus 1. The right side is the square root of minus 1 plus 2. That is the square root of 1, which is equal to 1. Minus 1 and 1 are not the same, so minus 1 is discarded. Next, we place x equals 2 into the original equation. The left side is 4 minus 2, which comes out to 2. The right side is the square root of 2 plus 2, so root 4. The square root of 4 is 2, and both sides agree. So x equals 2 is a true solution of the original equation. Now we check the candidate near positive 0.618. Its square is small, roughly 0.382, so the left side sits close to minus 1.618. A square root can never be negative, so no match is possible. That candidate is discarded, and a single candidate remains. We test the value near minus 1.618 last. Squaring it gives approximately 2.618. After the minus 2, the left side is near 0.618. On the right, x plus 2 lands near 0.382. The square root of that is also about 0.618. Both sides sit at about 0.618, so it survives. Decimals are only approximations, so we confirm this root exactly. The exact value is minus 1 minus root 5 all over 2. Squaring the top gives 1 plus 2 root 5 plus 5. That is 6 plus 2 root 5 sitting over a 4 below. Dividing through, x squared equals 3 plus root 5 over 2. Subtracting 2 makes the left side root 5 minus 1 over 2. For the right side, we add 2 to the exact value of the root. Minus 1 minus root 5 over 2 plus 2 gives 3 minus root 5 over 2. So the right side is the square root of 3 minus root 5 over 2. To pin that down, we square the number root 5 minus 1 over 2. The top squares to 6 minus 2 root 5, and the 4 below divides in. The result is exactly 3 minus root 5 over 2. And root 5 minus 1 over 2 is a positive number. So the square root in question equals root 5 minus 1 over 2. Left side and right side agree exactly. With no rounding at all, both sides equal root 5 minus 1 over 2 near 0.618, so the original equation has exactly 2 solutions. The first solution is the whole number x equals 2. The second solution is x equals minus 1 minus root 5 over 2. As a decimal, that second value is about minus 1.618. That completes the problem, with both answers checked in full. Thanks a lot for watching this solution through to the end. A like and a subscribe are always welcome on this channel. See you in the next video and enjoy the rest of the day.